we were looking at counting principles. We started off talking about the basic counting principle. Now we want to look at permutations of an entire set of objects. Here, first we need to see what do we mean by a permutation. Now, permutations are number of different arrangements of objects. Each arrangement is a permutation. So permutation is just another word we use for arrangement. We're going to consider two cases here when we're looking at permutation of an entire set of objects. Case one is that we only have distinct objects. So as an example, consider that you want to find the number of permutation or arrangements of the three distinct letters P, Q, and R. So we have three objects here. Now, for the first, now we want to arrange these three objects. So for the first object, we have three choices. For the second, for the first, we have three choices like any of P, Q, and R. For the second, we have two choices after we've chosen one over here. And for the third, then we have just one choice left after we have already chosen two here. So using the basic counting principle, if I can arrange the first in three ways, the second in two ways, and the third in one way, then the total number of ways I can arrange them together using the basic counting principle is 3 into 2 into 1, which can be written as 3 factorial is equal to 6. So now if we generalize this and say we have n distinct objects, then the number of permutations or arrangements of these n objects is n factorial. Because see, you have n objects. For the first object, you have n choices. For the second object, you have n minus 1 choices, and so on. And for the nth object, you have one choice left. And because of the basic counting principle, we can multiply them together, right? If we have n choices for the first one, and n minus 1 choices for the second one, and so on, and then nth one choice for the last one. So then, because of the basic counting principle, we know that together we have n into n minus 1 into n minus 2, so on till 1 is equal to n factorial different permutations, right? So, and the crux over here is, if all n objects are distinct, then they're n factorial permutations of all n objects. So case one was that all n objects are distinct. Case two is some objects are indistinct. For instance, if we have A, B, C, D, then the number of permutations or arrangements are 4 factorial, because the first object can be arranged in 4 ways, the second in 3 ways, the third in 2 ways, and the fourth in 1 way. So because of the basic counting principle, the total number of arrangements are 4 into 3 into 2 into 1 is 4 factorial. What if now some objects are indistinct, like we have like 2 ways here? Then the number of permutations of this is 4 factorial divided by 2 factorial in order to eliminate the 2 factorial permutations of A to avoid double count. Let's look at some examples. For example, PQR double P has how many permutations of 1, 2, 3, 4, 5 factorial, but divided by 3 factorial to eliminate the 3 factorial. Like over there, it was to eliminate the 2 factorial permutations of A. Here to eliminate the 3 factorial permutations of P to avoid double counting. Now, Sassen has now 8 factorial because 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. Because we have 8 objects, right? So it has 8 factorial permutations. So this 8 factorial comes from the fact that we have 8 objects. And then we have to divide it by the 2 factorial permutations of A and 4 factorial permutations of S to avoid double count. So permutation. So when we're looking at permutations of an entire set of objects, here permutation simply means we're looking at the total number of arrangements of this set of objects. The two cases here, all objects are distinct. In which case, if you have, say, n distinct objects, then the total number of arrangements or permutations are n factorial of all those n objects. And if some objects are indistinct, then you have to account for the permutations of those indistinct objects to avoid double counting.